Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wondered just how easy it might be to fake scientific results? Well, this new study dives deep into that unsettling question. Imagine this scenario: a really important medical trial, the kind that could help people with a serious illness, doesn't get the results they hoped for. The p-value, which is like a fluke or meter telling you how likely a result is due to random chance, was just a little too high, but then some of the data points were re-examined, and suddenly the result looked significant. It was enough to get a drug approved, but later, questions arose about the integrity of the trial. This wasn't just a handful of statistical tweaks, it involved changing the status of just a few patients. The researchers in this study asked just how much data tampering and what kind is actually needed to turn a non-significant result into a significant one. The study looked at 6 different ways someone could mess with data. Think of it like this: you have your data and you want it to show a specific result. Usually that something is significant, meaning it is likely not just a fluke. So you start tweaking. These 6 methods were like different tools for tweaking. Some involved dropping data points, others involved switching labels for data points, some involved changing values, and others even involved making up new data. They applied these to common statistical tests like the t-test, correlation, and chi-square tests, which are used in tons of research. Here is the crucial part. They started with data that genuinely showed no effect, the so-called true null hypothesis. This means any significant result they got afterwards was entirely due to the tampering. They ran simulations generating tons of datasets that were supposed to show nothing, and then they applied one tampering method at a time, targeting the data points that were most against the desired significant result. They kept tweaking, one data point at a time, rerunning the test each time, until the p-value dropped below 0.05, which is the usual threshold for statistical significance. And what did they find? It turns out not much data tampering is needed, especially in smaller studies. It takes surprisingly few changes to get a significant result. But here is something counterintuitive. Even in larger studies, the proportion of data you need to tamper with actually goes down. So the idea that a big study is automatically safe from data manipulation. It's kind of the opposite. A few tweaked points can have a bigger proportional impact in a large study than in a small one. Some of the trickiest methods, the ones that are hardest to spot, were also among the most effective. For instance, switching condition labels or repairing values. These methods don't actually change the recorded numbers themselves. They just move data points around or swap their associated labels. This makes them really hard to detect because if you just look at the individual variables, everything looks normal. The study found these methods were often among the cheapest in terms of how much tampering was needed. The paper's main conclusion is pretty stark. It's alarmingly easy and cheap to create statistically significant results from data that actually shows nothing. They found that even with median tampering of just 5 to 10% of the data in moderately sized studies, you could reliably produce false positives. This is where it gets really interesting. We often think of outright faking data as worse than, say, deleting data points that don't fit the desired outcome. Researchers often rate deleting data as more defensible than inventing it. But this study found that both fabrication and deletion, when done strategically to achieve significance, are equally dangerous. They both reliably create false positives from null data at a very similar and very low cost. Deleting inconvenient data points, even if you genuinely believe an effect is there, is just as problematic for research integrity as making up numbers in terms of its statistical outcome. Think about that vasculitis trial example from the introduction. 5 patients out of 331, just 1.5% of the sample, made the difference between a failed trial and a successful one. This study shows that 1.5% is not an aberration, but a typical cost for these kinds of manipulations. Now, the researchers were very aware that sharing this kind of information could be risky. They acknowledged that this knowledge could be misused. However, they argued that these tampering strategies have been known for a while, and what they're adding is quantification showing exactly how little is needed. They hope this awareness will actually help change scientific behavior by highlighting how impactful even a small number of tampered data points can be. So, what are the limitations? Well, the fabricated data in the study was deliberately extreme to show the potential for quick results. In real life, someone trying to be more subtle might use less extreme fabricated data, which might be harder to detect, but perhaps require slightly more tampering. Also, the study used data that was perfectly null. meaning it showed absolutely zero effect. In reality, there might be a small true effect that researchers are trying to top up to significance. This would likely make it even easier to get significant results. Ultimately, this study is a wake-up call. It shows that the boundaries between questionable research practices and outright fraud can be very blurry, and the effort required to cross those boundaries can be surprisingly small. The methods that preserve the appearance of normal data distributions are particularly insidious because they're harder to spot. This really emphasizes the need for robust data auditing and transparency in research, so we can trust the scientific findings we rely on. This research is fascinating because it quantifies something we often talk about qualitatively. It's not just about the intent of the researcher, but the undeniable statistical consequence of manipulating data. It highlights that what might be perceived as a minor tweak by one researcher can have a significant impact on the validity of the finding. Future research could explore more sophisticated detection methods for these subtle manipulations, especially those that don't alter individual variable distributions. What do you think about these findings? Does it change how you view scientific results? Let me know your thoughts in the comments below, and if you found this breakdown helpful, please give this video a thumbs up and subscribe to RUBIN'S Mind Lab for more science explained. Simply, we'll see you next time.